and welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to continue our discussion of the mixed level factorial designs, and we're even going to look at some R code that's going to help us construct these designs because they're kind of a pain to deal with. All right, so in today's lecture, we're going to continue our study of the mixed level fractional factorial designs. There's a lot of adjectives in there, so it's kind of hard to keep track of. Anyway, what we're going to do is we're going to look at two specific examples, combining 2-level and 4-level factors and combining 2-level and 3-level factors. Now, 2 and 3 are relatively prime. That's going to make it a little bit harder to combine. But 2 and 4 are not relatively prime, and it turns out that we can actually start with a 2-level factorial design and sneak in some 4-level factors in there and be able to test all of them. And how do we do that? Well, we're going to find out all of that in today's lecture. So let's jump into the notes before the traffic comes and you can't hear me anymore. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we are going to continue our discussion of mixed level designs and to actually look at some specific examples, that is mixing 2-level and 4-level factors and 2-level and 3-level factors. And we're going to see exactly how that works and kind of the pros and cons and where we can run into some trouble, and also kind of the nifty little tricks we can do to save on sample size. And then that shouldn't take the whole time. So after we're done with that, we'll actually look at some R code, which will design experiments for us, because now that you've more or less gone through most of the course, you'll find out that a lot of these experiments can just be created in R and probably other stats packages as well. But it's always good to know exactly what's going on behind the scenes before you just let a computer program decide what experiment you should run. All right, so we're going to get right back into it and look at those orthogonal arrays from last time and mixed level factors. So let's get into the notes. All right, so today's lecture is on mixed level designs. And the first one we're going to start with is the idea of a 2 to the, well, I guess the way I wrote it was 2 to the n, 4 to the m, though now that I think about it, I don't really like that because n is usually our sample size. So maybe we'll just say a 2 to the k, 4 to the L, for lack of a better letter design. So what we want to do is we want to mix binary and 4-level factors together. And as I mentioned, I think in the last lecture, one way we could do that is just kind of tensor product the whole thing, which basically means for every combination of my binary factors, I will have every combination of my 4-level factors. And that can work, but it can also be absurdly large. And we have to be careful that our sample size does not get too big or bigger than necessary to get done what we want to get done. So what we're going to talk about first is the idea of the method of replacement, which is a way to turn a 2 to the k design, factorial design, into a 2 to the k, I guess I'll say k prime. I'm going to run into trouble with all these different variables, but it's a different k, and 4 to the l design. So again, the idea is that rather than just trying to combine all different levels of your factors into one super design, which will have a massive sample size, we're going to start with a 2 to the k design on its own, and then we're going to start to confound columns with the 4-level factors, no matter depending on how many we have. So how are we going to do that? Well, roughly, the idea is that we will, maybe I'll say 1, start with a 2 to the k design. And then step 2 is pick 3 columns. Now remember, every column in the design is going to correspond to a main or an interaction effect. In a 2 to the k design, they each require 1 degree of freedom. For a 4-level factor, you're going to need 3 degrees of freedom to test that, and hence we're going to need 3 columns to confound in order to take that 4-level factor and shove it into our 2 to the k design. This all works because 4 is a multiple of 2, or is a power of 2. Otherwise, we'd get into trouble if we had something more complicated, like, well, even 3 is going to be different, which we'll see in a second. But if instead of 4, we had 5-level or 6-level factors, we'd run into a little bit more trouble. But here, the idea is that because 4 is 2 times 2, you can actually get away with hiding 4-level factors within a 2 to the k design. So what I want to do is I want to pick 3 columns. I'll say call it alpha, beta, and their interaction, alpha, beta. So here, alpha and beta are just columns. So I'll say, maybe I'll give an example. For example, we could pick something like alpha is equal to 1, 2, and beta is equal to 3, 3, 4, and then alpha beta would be the 1, 2, 3, 4. So those would be the 3 columns: a 2-way interaction, a 2-way interaction, and a 4-way interaction. So the idea is that we pick these 3 columns and replace them, i.e. confound them, with 1, now I'll write it out just because there's too many 1s and floating around, with 1 4-level factor. And the way we do that is, well, simple enough. What we do is we consider our columns, alpha, beta, and the interaction alpha, beta. Now in these columns, there's really only, I guess, 4 different entries that you would see, right? You would either see dot, I think I had it slightly backwards in the way that I did it in my notes, so I'm going to switch it to be, well, I'll do minus, minus. We'll do minus, minus, plus, minus, plus, minus, plus, minus, minus, and plus, plus, plus. So, right, if you have a setting for column alpha and a setting for column beta, which is either plus or minus, then you know what the setting for alpha beta is going to be. It's going to be the product of the 2 of them. In my online notes, if you're reading those, I did it more like binary arithmetic. So minus minus gave me a minus, whereas here I want to do it like multiplication to try to stick with what we were talking about earlier. So minus times minus is a plus. But it doesn't really matter as long as you're consistent in the way you define it, because plus and minus are arbitrary symbols that just correspond to our 2 different factor levels, right? Anyway, the idea is that if we were to just isolate columns alpha, beta, and the interaction alpha, beta, we would have entries that look like one of these 4 rows. So what we do is we assign each of these to some factor A, which is going to be my 4-level factor. So we can just assign these using maybe the binary representation to get 0, 1, 2, and 3. And that's more or less it. So what we've done is we will, in some sense, remove columns alpha, beta, and alpha, beta from our design and replace it with an A, where A takes on 4 levels. And what we've effectively done, right, you can't really remove the interactions, you're confounding the interactions. So these interactions still exist, but hopefully those interactions are not significant, or else there would be some ambiguity there with these factors, the two-way factors, the two-level factors, and the four-level factor. So it's always good to basically, I'll note that here we want alpha, beta, and alpha, beta to not be significant. Or else, yeah, there could be some issues, because if you found that factor A had a small p-value, you'd want to say that that's because of factor A and not because of the alpha beta. So if these interactions are high order, again, if alpha and beta and the interaction are all like fourth order interaction or four-way interaction terms, then it's probably safe to say that, yeah, they're not going to be significant. Or if we have to choose whether a four-way interaction or whether a main effect is significant, we would just default to the main effect and assume it's not, the significance is not coming from a four-way interaction. Anyway, that's more or less the whole idea. Now, there are some, quirky little things that go on here. And then the point is for 3, we can repeat this with 3 new columns to insert more 4-level factors. So we can do this more than once. In fact, you can, in some sense, completely saturate the model with 4-level factors, and then you have more like a 4 to the whatever L or 4 to the K factorial design, and you've obliterated all of your 2-level factors. Now you can do that almost. So let me make sure I get this right, because it changes depending on how many times you can iterate this, right? So yeah, basically, let's take it to the extremes. Taken to the extreme, as we like to do in statistics, especially, I guess, extreme value theory, which is all about extremes, but that's another course. Effectively, every time, what are we doing? Well, every time we insert a 4-level factor, we remove 3 columns. So what does that mean? Well, that means my 2 to the K minus 1 columns are in my 2 to the K factorial design. Now, if I continue to do this, and basically now if K is even, then it turns out that 2 to the K minus 1 can be written as 4 to the L minus 1, right? Where L is just half of K. So it seems like we should be able to cram a whole bunch of 4-level factors into a design matrix or a design table that originally has a bunch of 2-level factors in it. And the idea is that basically it is proven, not by us and not in this course, that we can decompose, or maybe decompose the way I want to say it. Yeah, I guess that's way. We can decompose a 2 to the K design into 2 to the K minus 1 divided by 3 sets, or I guess to be precise, mutually exclusive we'll do an example of this too to explain what's going on. Sets of 3 columns to become a, let's say, 4 to the L design. All right, so the idea is that if K is in fact even, if we start with a 2 to the K design where K is even, then we can keep pulling off groups of 3 columns to replace with 4 level factors. And what we end up with is that therefore any orthogonal array of the form, basically what I have is if I have 2 to the K rows in my array, and what I'll have is something that's going to look like 2 to the m minus 3n, where m is the number of factors that I'm starting with, and 3n is the number that I've taken away and turned it into 4 to the n, with, I guess, whatever strength. Doesn't really matter for this. The point is that I can kind of, any orthogonal array of this form exists. So I can try to combine my two level factors and my 4 level factors in just 2 to the K data points. So that's nice. It means that I can, again, hide these 4 level factors in a 2 to the K factorial design without having to increase my sample size. Now, if K is odd, we can kind of not almost get there. If K is odd, then it's been shown, been proven that we can only get, it's 2 to the K minus 1 divided by, I think it's, oh no, K minus 5 over 3, sorry. 2 to the K minus 5 over 3, we'll say mutually exclusive column sets. And this was actually proven by, I think, Jeff Wu in 1989 in the paper that I cited on how to construct a 2 and 4 level mixed, or a 2 and 4 factorial mixed level design. But roughly, yeah, the idea is that so you can almost get any design you want if K is odd, but you can't take it to the extreme of basically cramming all your 4 level factors in there. So you're going to have a couple extra columns that don't quite line up when you use this method of replacement that we talked about up here. Okay, so yeah, let's try. Well, I'll just copy over an example so you can see exactly what's going on here, because I think that would be the best way to explain this. So what we'll do is we'll copy over an example. And the example is a 2 to the 4 factorial design, and it looks something like this. So here's my 2 to the 4 complete factorial design with all of the columns. Now, if you've noticed, I've arranged the columns a little bit differently than we usually do. Normally, I start with the main effects, then I do the 2-way interactions, 3-way and 4-way, and so on. Here, I've kind of grouped them 1, 2, 1, 2, 3, 4, 3, 4, and so on. And there's a reason for that, because every set of 3 columns, starting from the left and going to the right, is going to be in that form, alpha times beta. So 1, 2, 1 times 2, and 1, 3, 2, 4, 1, 2, 3, 4, and so on. And what that means is that we could actually take this design and replace it with 5 4-level factors. which would look something like this. Right, so what we'd be doing here is using the method of replacement, and I'd effectively be grouping these three columns together of like this, and then using them to then insert 4-level factors. And so on, right? I'm not going to keep drawing these arrows because it's going to start to get a little messy. But roughly what we have here on the wall on the left-hand side, we have is a 2 to the 4 design. And on the right-hand side, I guess is, well, a 4 to the 2 design, or a 4 to the, we'll say, k minus k minus 2 for k in what, I guess, 2 through what, the highest I can go up to is 5. So I find, yeah, I guess 5, 2, I'll just write it out, 3, 4, and 5. So similar to the prime level designs that we talked about last time, remember I said, if you have a prime number, things are really easy to do. I can just write out a big, prime number to the k factorial design. We did 5 to the k and 7 to the k last time. When you're dealing with 4, it's a little bit more complicated, but if you recall what I said last time, if the factor level is a power of a prime, like 4 or 8, which is 2 to the 2 and 2 to the 3 respectively, then I can still create a nice full factorial design like this. And here, it just, the difference between a 4 to the 2 and say a 4 to the 3 minus 1 would be how many of these columns correspond to main effects, right? Because what I could do is I could start by inserting, let's say, factor A in here and factor B in here. And then what I would find out is that I'd actually get an interaction column, which would be, I think, A plus B if I did this correctly. Yeah, just quickly scanning down the columns, it looks like that's, and actually I can just do it over here because 1 times 3 is 1, 3, and 2 times 4 is 2, 4. So this would be the interaction. And then I guess these other ones would be some other high, maybe something like AB2 and AB3, though I didn't double check that. So I would need to check that to make sure that I'm actually getting the right. Oh, wait, no, sorry. You can't actually include AB2. Yeah, I forgot. There's an issue here. These interactions are more complicated because of the four levels. But at the very least, I think the first interaction is in fact the sum of the first two columns mod. Actually, no, wait. 3 plus 3 is 6, and 6 mod 4 is 2. Nope, never mind. All right. Forget that. I'm going to leave it in because I think it's instructive to point out that these are interactions, but not like before, in the sense that we're not just adding the columns together, because 4 does not give me a finite field, and that means that if I try to just add the columns together, things go a little bit wrong. Mod 4. I want to only do that when I have a finite field, which is when the number of factor levels is prime. Regardless, we can still test this, right? I can have A and B, and I could even include other factors as well, like C and D and E if I really wanted to. So it all depends on how many 4-level factors I want. I could also do a mix and match kind of deal, right? I could keep, say, the first set of 3 columns here if I want 1, 2, and 1, 2, and then I could turn the rest of these into 4-level columns, and then I would have 2 binary factors and 4-level factors, right? There's a lot of different ways that you can imagine transforming one into the other and back again. But actually, my confusion that I quickly had about how to think about these interactions is a good thing
to discuss, because, yeah, what are the contrasts for a 4-level factor? Well, as I said, we can't just kind of add these together to get an interaction, but we can do some other kind of quirky things that are interesting. So first of all, if ordinal, we can use polynomial contrasts as usual, as before. So right, in this case, we would have 4 factor levels, which would give us a linear, a quadratic, and a cubic a polynomial fit. Cubic's not so high that you might get something cubic in your data, so it might be worth. If not, or even if so, we can consider alternative, missed the N there, contrasts. So one system of contrast that they propose, I think, in the textbook that often shows up is the idea of having contrasts A1, A2, and A3, right? We have 3 degrees of freedom, so we can have 3 different contrasts to look at a single 4-level factor. And here what we would end up with is a -1, -1, +1, +1, a -1, +1, +1, -1, and a -1, +1, -1, +1. And the idea here is to split, or to group, maybe I should say, not split, group the 4 levels into each pair of 2s, which, yeah, as English goes, that might not make a lot of sense, but let's do an example. So, all right, so here I have my factor A, which is going to take on the value of 4 different provinces: British Columbia, Alberta, Ontario, Quebec. So sorry, all the other provinces in there. I didn't mean to exclude you, but we just need 4. So I thought, let's pick 2 on the left, 2 on the right. And then we could imagine running an experiment where our response was something like the number of people vaccinated per capita, or something like that, to say, oh, are they all vaccinating at the same rate, since that's what's in the news these days. And if we looked at these contrasts, what we would be doing is we'd effectively be grouping up the provinces. So the first contrast, A1, would say that we have basically BC and Alberta, and versus, maybe I could say minus, but I guess the minus sign's on the other, so we'll just say versus Ontario and Quebec. And then A2 and A3 similarly would pair up the provinces differently. A2 would be, I guess, BC and Quebec versus Alberta and Ontario. And then A3 here would be BC and Ontario versus Alberta and Quebec. So if you took your 4-level factor and you decomposed it into these 3 contrasts, we would have different groupings. So what we might find, for example, is that factor contrast A1 is the most significant in our study because it's grouping 2 Western provinces and 2 Eastern provinces together. Or maybe not. Maybe you found that another one of these contrasts was significant, and it would tell us that for some reason, these 2 pairings are, significant in some way compared to the other pairings. So this is one way that you can look for different types of contrast for a 4-level factor. And if you had, I'm not going to write it out because it'll be a real big mess, but if you had another 4-level factor that we could, make up, then what you could do is then you could try to cross the contrast, right? Because if you have one 4-level factor, we have 3 degrees of freedom. If you have an interaction between 2 4-level factors, you now have what? You have 9 degrees of freedom, which would correspond to 9 different contrasts. So you could imagine contrasting all possible pairings of pairings, which would be a real mess to write down, but at least it gives you something intuitive that you could, or maybe not intuitive, but interpretable. And that's what's nice, because so often, like we talked about before, when you have these higher order interactions, it can be very hard to interpret what the output is anyway, which is one of the reasons why we typically don't care about testing for high order interactions, because 1, they typically aren't interesting, and 2, even if they are interesting, we don't know how to interpret them anyway, so who cares, right? Anyway, yeah, that's more or less everything I wanted to talk about 4-level factors. I have some more examples. We kind of did these already, though, where I say that you can't just add them up mod 4, so maybe I'll just put a warning, which is adding mod 4 is troublesome because 4 is not prime, which means I don't get a finite field, which means I don't have inverses, which means bad things happen. And I have some examples, but I wouldn't worry about it too much. The point is that there are ways to consider 4-level factors, just not in the way that we were treating 2, 3, 5, and 7-level factors. So we just have to be a little bit aware of that. Anyway, what I wanted to get into is the so-called 36 run design, which will be the next topic, which is basically how to combine 2-level and 3-level factors into, or maybe I should say with only 36 observations. 36 chosen because, well, it's 4 times 9, so it's 2 times 2 times 3 times 3. And because it's a reasonably moderately sized sample, right? You can imagine, okay, 36, that seems like a good sample size. Now, okay, you could double that if you really wanted to. You could do a 72 run design. There's a lot of, but just for the sake of the explanation here, what we're going to do is we're going to consider 36. So to start, we can, I'll say, tensor a 2 to the 2 and a 3 to the 2 together. And what we end up with is something that's going to have 36 observations. And it's basically, we're going to take 2 tables. That is, we're going to have something like A, B, and AB, which is going to be minus, minus, plus, again, minus, plus, minus, plus, minus, plus, and plus, plus, plus. So we would take our 2 to the, this is our 2 to the 2 design, and then we would have our 3 to the 2 design, which would look something like D, E. I'm not using C because I'm going to eventually try to throw a C in here and confound, or I guess alias it with AB to be precise in the terminology. And then we'd have a D, E. And in this case, right, we would have 0, 0, 0, 1, 1, 1, 2, 2, 2, 0, 1, 2, 0, 1, 2, 0, 1, and 2. And if we combine these, 0, 1, 2, 1, 2, 0, 2, 0, 1. I think. Yes. I got something slightly, oh, that's right, of course. And there's one more column. I'm like, what am I missing here? Yeah, there's another column, DE squared. So if we just go back here and we say then it's 0, 2, 1, it is, I guess, 1, 0, 2, and it is 2, 1, 0, if I got that right. Let's hope I got that right. Anyway, the idea is that I could take these two tables and I can combine them into one super design, kind of like I said before, which would have columns that look like A, B, D, E. I should give a space there. D, E, DE, and DE2. And then I can just start filling them in, and they'd be whatever. They'd be like plus and minus, and then let's say 2 and 1, and then whatever 2 and 1 combined to get 0 and 1, etc. And in this case, I would have my 36 observations. Now, again, what I said at the beginning was we don't always want to do this, just combine a 2 to the 2 and a 3 to the 2. But when you have factor levels that are relatively prime, the fact that 2 and 3 do not share any common factors, unlike 2 and 4, there's no convenient way to like slip a 3-level factor into a 2 to the k design, because again, 2 and 3 just don't mix like 2 and 4 do. But we can still start with the idea of a 36 run design, which would be the combination of a 2 to the 2 and a 3 to the 2. And then we can start to alias in other factors if we really wanted to. Like, again, I could plug a C in for my AB. I could plug a, I guess, DEF in here, and I could even plug a G in here if I really wanted to. So again, there's nothing too profound going on here. The point is I'm going to combine a 2 to the 2 or 2 to the 3 minus 1 with a 3 to the 2, a 3 to the 3 minus 1, or a 3 to the 4 minus 2 design. So basically pick one from column A. Well, I guess I'm reusing A and B here. Pick one from the first group, pick one from the second group, and combine them to get your 36 run design. Now, there are some issues in the sense that you can get some pretty crazy defining contrasts and things like that. So, for example, basically the DCSG, the defining contrast subgroup, is complicated, to say the least. So, for example, if I considered my 2 to the 3 minus 1 and my 3 to the 3 minus 1 with A, B equal to C and D, E equal to F, like I did above, but let's say we ignored G, then what I end up with is, well, I have, what's my defining contrast subgroup look like, right? First, I'm going to get an ABC for the first guy. I'm going to get a DEF squared for the second guy. I have to multiply these two things together to get an A, B, C, D, E, F squared, and then I also have to multiply them together while squaring the 3-level term to get an A, B, C, D squared, E squared, F, which is unique from the first 6-way interaction. So yeah, things can definitely get a little bit complicated when you're dealing with this, but roughly you should be okay if you just kind of combine one of these 2 to the whatever designs with a 3 to the whatever design, and then you can test some amount of factors from 2 or 3 2-level factors and 2 to 4 3-level factors on 36 observations. And again, it's nice to try to keep that sample size small. Now, Yeah, there's a lot of complications there can be some complications when we look at things like the contrasts and whatnot. But honestly, I don't think it's really worth getting into all of those details. This is more or less the idea that I wanted to leave you with. Now, what I want to do is, before we get on to the next topic, which is non-regular designs, which is a whole nother fun thing to look at, I want to jump into some R code, and I can show you kind of how these things work. Well, how you can design your own experiments using R packages. And this is going to actually be quite useful because, as you can see, if you take one thing away from this, it's that designing experiments is kind of annoying because you have to worry about all these factors and aliasing and confounding, and do I have a big enough sample size to test what I want to test? And if I'm testing one factor, is it actually aliased with another factor that I meant to test, and et cetera, right? It can kind of give you a headache. But there are packages that can help you, and we're going to look at those right now. And we're back, and we're going to talk a little bit about how to actually design an experiment in R. That is, if you want to design an experiment, you can use some packages in R that will allow you to, it will basically give you the entire design matrix and tell you what you need to do with it. So the first function that I want to look at is the frf2 function, which is in the frf2 package. And this one will basically produce a fractional factorial design with binary factors in it. So it doesn't give us any possible mixed level design. We'll talk about that with a different function, but it does do a really nice job of producing, fractional factorial designs. So if we want to look at an example, right, we can do lots of different things here. What I could say is I want to do, let's say, 16 runs. So my sample size and runs here is 16. And maybe I want to tell it that I want to test 5 factors, not that. Let's say I want to test 5 factors on 16 observations, right, rather than 32. And up there we go, I got one. And it already has done a couple things. One is it's decided how to alias. And 2, it has also, in this case, randomized everything. So if you notice, I'm not starting off with like all ones followed by the next ones down. In this case, what it does is it completely randomizes the order. So something that we talked about, I think back in day 1 of this class, is that when you do one of these designs, you don't want to do it like it is in the textbook and then go row by row. What you'd want to do is you would want to randomize your rows. And here the R function does this by default. I think if I run this again, I should get a different output of columns. So, subject 1 now, it looks like, is getting only medication 1 in this study, whereas up here, he would get B and C and D in this cocktail of drugs, assuming that there's 5 different drugs that will be cramming down our 16 subjects' throats here in this hypothetical study. So you can, if you want to just see what it looks like otherwise, you can tell it to not randomize. And in that case, you get something that looks a little bit more standard. In this case, again, we have deleted some columns, or some rows, that is. We should have, right, 32, but in this case for my 5 factors, but we're only doing it on 16 observations. So we have the all ones row. We don't have the all minus ones row. If I were to increase this to 32, I think we should see everything then in the usual order, right? All minus ones, then we get a 1, then we get a 1, then we get 2 ones, etc., all the way down to the all ones row at the bottom. And it says, oh, by the way, this is a full factorial design. It's like, yeah, we know that because we've been doing design of experiments all term long. But if we go back to this design, it's a little bit interesting, right? The question might be, well, what did it alias, right? Well, it turns out there's a nice function beyond this code that I wrote, which we'll look at in a second, which is called aliases. And aliases will tell us exactly what all the aliases are in our design. So what you do is you give it a linear model, and it will tell you what the aliasing is. And then there's a couple other arguments here that we don't really care about. But in this case, what I can do is I can, well, like I did up here, I'll just call this DesMat for design matrix short. And then what I can do is I can fit a trivial model, trivial in the sense that I'm just going to go AOV, and then I'm going to give it 16 random normal this is going to be my response, my 16 random normals, which really have nothing to do with anything. I'm just using them as a place filler. And then I can use a shorthand, something that I forgot to mention, I think, earlier in the course when we looked at some examples. If I have factors A through E, I could write A plus B plus C plus D plus E, but that's kind of annoying. Instead, I can just put dot, and dot will take care of it for me. And then I can just say dot to the 5 because I want to test all my factors. Now, R only knows what dot is if I give it a data set. So my data set is going to be my design matrix, DesMat. And then what happens when I hit enter? Well, we get a whole bunch of aliasing relations. Actually, something looks a little different. Nope, maybe that's fine. Yep, there it is. Nope, never mind. We're good. We have ABC, the three-way interaction, which is aliased with DE. There it is. Okay, good. So yeah, basically what we can do is we can work we can work backwards, and what we can find out, well, actually, no, we don't even have to work backwards. It tells us right here, the intercept term is aliased, which is kind of like the identity, is aliased with the 5-way interaction. So the function fr f2 is smart enough to know, if I have a 2 to the 5 minus 1 design, the best thing I can do is just alias the 5-way interaction with the identity, in this case, the intercept term. Yeah. In this case, I think there's not much else more to say. We can look down the main columns and say, we have all our main effects here, A, B, C, D, and E, and we can find out that they're all aliased with 4-way interactions, and so on. Now, if we tried to make this design a little more complicated, so let's say, for example, we tried to reduce this down to 8 observations, well, what happens? First of all, we can look at our design matrix, and we get this nice short little design matrix here, but the question is, what happens with the aliasing? Well, in this case, if I, just run this same code again, I get an error. Great. Because I'm supposed to put an 8 in here, because I've reduced the sample size to 8, so my dummy response variable needs to change. Okay, so now we get, more things. So notice now the intercept is aliased with a couple things. We have an ABD, we have an ACE, and we have a BCDE. So it just chose that for us as that's the defining contrast subgroup. Now, it did that because it's still resolution 3. It could have picked other terms to shove in there, but as far as this is concerned, A through E are all interchangeable. So they have no physical meaning right now. So it just, presumably randomly selected these, because if it did it alphabetically, it would have chosen A, B, C as the first one. Okay, I don't know exactly. It's probably, actually, we can know if it's going to randomly select it, because we could just run the entire thing again and see if it gives me a different defining contrast subgroup. So if I regenerate the design matrix randomly and I say alias, it gave me the same one. Interesting. So however it decided on this. Of course, it would be up to you as the experimenter to decide what A, B, and C would correspond to in your study. Regardless, what we find is we have a resolution 3 design. We can quickly go check our main effects and find out that A, for example, is aliased with CE. It's also aliased with a 5-way, 5-way interaction, yes. and another two-way interaction. So again, it's resolution 3. Our main effects are not clear in this case. In fact, are any of them clear? That's kind of interesting, right? We know that A, B, and D can't be clear, and A, C, and E can't be clear, and that's everything. B, C, D, and E. Yes. Okay, so yeah, nothing's clear in this case. No, yeah, of course, because you'd have to have 2 3-way interactions, and they would cover all of your main effects. So yeah, that's what you get. Anyway, it's a neat little function, and it will help to quickly figure out what's going on with your design. So you can decide, if this is a good design to run, or if I need to increase my sample size, etc. Now, there's another thing I wanted to mention, which is we don't have to give it the number of runs. We could just give it the resolution. And I think this is a really nice feature of this function, that if we go back to the documentation, I can give it the resolution instead. I can give it a lot of other things, like I can give it generators and, other aspects, blocks as well. But in this case, let's say I want a resolution 4 design. So I don't want to have those 3-level factors. Instead, I want a resolution 4, and it should give me, I think, 16 observations, right? Yep, so there's my 16, and I can go back to it. I can go back here, and I can look at the aliasing relations, and what I find out is that I actually have a resolution 5 design, because on 16 observations, the resolution 4 and the resolution 5 can both be achieved on 16, and neither of them can be achieved on 8. So what that means is that it says, well, I might as well just do a resolution 5 because it's the best choice given 5 factors. So in this case, it kind of fixes your problem for you in a sense. It says, you wanted a resolution 4, but on the same data size, I can give you a resolution 5. So I'm just going to do that because that's the smarter way to do it. Again, it's kind of a neat function. It's really nice to be able to plot everything out here for you. Now, what I also wrote is this neat little function, which is going to calculate the sample sizes based on the resolution. So what this thing is going to do is I can give it factor levels and say, or the number of factors in my design. I'm going to start at 5 because if we go under 5, it becomes kind of boring. But we can go from 5 to let's say 24. So I might want to do a 2 to the 5 design. I don't want to do a 2 to the 24 design because, 2 to the 20 is a million-ish. So 2 to the 24, I guess, would be, 2 to the 16 million-ish if we just keep multiplying, since 2 to the 4 is 16. So anyway, yeah, you would never want to run that. But typically, we don't really need to go beyond a resolution 5 design, right? Because resolution 5 design means that all of our main effects are strongly clear and all of our 2-way interactions are clear. That's usually about as good as you need it. Going beyond that, again, you're not typically worried about 3, 4, and 5-way interactions. So what I did with this function was said, what sample sizes would I need? And it should give me a nice plot, and I didn't actually save the output, so it's probably going to just spit out a whole bunch of output now. Let's see. Yep, there's my table. Anyway, this is the output in this plot. And what it is, on the log scale, notice on the horizontal or the vertical axis, I have my number of factors here, and on the horizontal axis. So if I have 5 factors and I want a resolution 3 design, that means I need 8 observations. But if I want a resolution 4 or 5, I'm going to need 16 observations. It's all powers of 2, but R is doing this in 10 and 20 for the axis. Anyway, what happens is as we increase, right, our number of factors, we can get up to 10. So, right, a 2 to the 10 design would take 1,000 data points. That's a lot to collect. But if I want resolution 3, I can get it done with 16 data points, which is awesome. And if I want to go a little higher to resolution 4, I can get it done with 32. And resolution 5 at 128, which is, again, it's all powers of 2, so I can take a guess at what number it is. And going even further, you can see how resolution 5 starts to diverge a bit from the other ones. If I have 20 factors, right, you're never going to do a 2 to the 20 design because that's a million observations. That's kind of crazy. But if I want a 2 to the 20 design that's resolution 3, then I can get away with that with only 32 observations, which is kind of neat. That means that if I have 32 data points, I can test 20 different factors on it and still have a few degrees of freedom left over for a couple two-way interactions. If I wanted to go all the way up to resolution 4, I can do that. I just need to double my data size, and I end up with 64 data points. Now, if I want to get to that magical resolution 5, which is about as strong as we ever really need, we would have to massively increase the data. It would be up to 512 data points. So you can see here that even though a resolution 5 design will reduce the total amount of data a lot, right, from something stupid like 1 million data points to only 512 data points, it still requires a pretty big data size to run. Whereas the resolution 3 and 4, you can get away with like a really small data size, and that's a big win. Now, yes, in this case, you might notice that our sample size is always going to be a power of 2. And I think it even says that if we go back to this package, well, maybe, the number of runs, yes. So the number of runs must be a power of 2, i.e. 4 to 4096, because it's probably like, I'm never going to want to collect that much data. What happens if you don't want to do a power of 2, right? If you don't want to do a power of 2, like if you have enough money to collect, say, 30 data points, but they're not going to give you those extra 2 to get to 32, or you have something strange like a 24 data point or subjects that you can test on, well, that's where the Plackett-Bergman design comes in, which is a non-regular design. That's going to be in the next lecture, and we'll discuss how that works there. But we are not done completely yet, because there's a couple more neat little tools that I want to show you about in these R packages before we move on to the next lecture. The other is this library, or this package called ConfDesign, which is a confounding, a library with some functions that will allow us to do confounding. So, or basically to understand the confounding in our design. And this is quite neat, right? Here we have, if we use the function confset, what it'll do is it'll tell us what we've confounded if I give it a basically a matrix, a matrix whose rows define the effects to be confounded, and then P is the number of levels for each factor. Now, the number of levels for each factor must be prime, again, because if you have non-prime levels, things get a little messy, as we discussed already. And I think they all have to be the same. So this would not work for a mixed level design, but it would work for a 2 to the K, a 3 to the K, a 5 to the K, but not a 4 to the K or a 6 to the K design. And what you can do, so this is the example they have here. I can say, okay, what I want is I want G, and G is just going to tell me what my confounding blocks are. So I chose, this is what they have in their sample code down here, but we'll do some more extreme examples in a second. Here, what they say is I have 3 level factors, and my first block is going to confound A, B squared, C, right? That's one of the 3-way interactions. Meanwhile, my other one is going to confound B, C, D, which is another 3-way interaction. And if I plug it into this function, what it'll do is it'll give me this thing where what it says is, you confounded these 2 3-way interactions. That's going to result in 2 more 3-way interactions being confounded. So again, a really nice tool to use because you can quickly find out all of the confounding relations. Probably should have told you about that when you were doing your assignment, but it's much more fun to work it out by hand, right? Anyway, you could include, let's say, 3 blocks. Then the question would be, well, man, what should that third block be? I mean, I could just try something like A and maybe A, B, C, D, but I have a feeling that's going to be a bad idea. And then if I say this, well, now we get lots more confounding, right? We've gone from 4 to 13, just like we saw when we discussed 3 to the K minus Q fractional, or 3 to the K factorial designs in this case. But what happens? Well, if we scan through really quickly, we see, we lost a two-way interaction, but oh, there's the problem. We lost a one-way interaction. We lost a main effect A. So main effect A has been confounded, and we're sad about that. So we'll have to try a different thing. And maybe we can try picking out a two-way interaction like AD and see if that saves us. And in this case, we can scan through the columns and say, oh, it's 3, 3, 3, 2, 3, 4, 3. Oh, well, we lost C. Oh, no. So yeah, as I mentioned in other lectures, choosing the right terms to block by, the right factors to block is hard, and it's not always straightforward what the right answers are. And it's very, very easy to just pick 3 that seem reasonable, and then you end up losing a main effect and you're sad. So you can use functions like this to test out different blocking schemes. Now, if I really wanted to, I could also take this to a more extreme. I could, for example, add in an E and an F. I'm running out of room here, so let's expand this a little bit. So I can add in maybe more terms. Now I have 6 factors in my design, and I can even take this beyond 3 levels, that is, right? I could give this like a 3 and this a 4, and then I can tell R that what I actually want is a 5-level factorial design. And then it comes up with this crazy thing and says, well, if you want 3 different blocks, all with 5 levels, and you cram them all together, this is what you're losing in your design. And then we could scan down and try to see if, well, actually, no, it's funny. We could probably do this really fast in code, because what I could just say is, are these equal to 0? Or let's say greater than 0, and then row sums, and that'll tell me exactly what the interactions are. And then what I can even do here is I can wrap this whole thing in a table, and it'll tell me how many of each interaction I've confounded. So there, I lost 2 3s, 2 3s, 9 4s, 12 5s, and 8 6-way interactions. So yeah, again, sorry I didn't tell you about this when you were having to do this manually for your assignments, but yeah, it's quite a neat little way that you can quickly find out what you're confounding. And you can spend a lot of time playing with this. I'd encourage you to try it yourself and just see what happens, right? Because there's a lot of interesting tools you can use here. Okay, so what did we do? We did confounding, and we did for prime level designs and prime level factorial designs, and we did how to construct a 2 to the K minus Q fractional factorial design and look at the aliasing. There's one more thing I wanted to mention, which is the topic of today's lecture, and that's how to generate a mixed level design. Now, these are a lot harder to come up with. There is a function hiding in the DoE base package called factdesign, and this one will give you a full factorial design with arbitrary numbers of levels. So this one is not going to be able to do fractional designs, because fractional designs are really hard for mixed levels. Typically, the easiest way to do it would be like we did for the 2 and 3 level mixtures, where what we do is we create a fractional design for the 2-level factors, a fractional for the 3-level factors, and we cram them together. In the 4 case, what we said is that we can actually do better, because for 4-level factors, we can sneak them into the 2-level design. But nevertheless, what you can do is you can just create one giant design using this fact.design function. And here, what I can say is, okay, well, what are the levels that I want? Well, I could have, let's say, a 2, a 2, a 2, a 3, and a 5. Is that what I want, or do I want number of factors can be? Oh, I think I can also, there's different ways to, I think that's what I want. Let me double check the documentation, as I did not pre-write this code. Yeah, I want n levels. I can also add in blocks, but let's not do blocks. Basically, I can hit enter and I get my full factorial design with all these wonderful inputs. Now, if you notice, it's doing these starting at 1. So my binary columns, which are A, B, and C, have the entries 1 or 2. Column D is a 3-level factor column, so it has 1, 2, and 3 as the entries. And column E, the 5th column, has 5 levels, so it runs from 1 to 5, because that's the way they've decided to default this. Now, you can change it if you want by actually giving factor names. I'm not going to go through all that because it's not really worth it. But it does tell you, oh, look, I can give you a full factorial design. It's going to have 120 runs, which is presumably 2 times 2 times 2 times 3 times 5, which, yes, it is. So again, if you wanted to try to be more efficient, you would have to go back and think to yourself, well, how can I fit these factors together in a better way? The only way here, I think, would be to try to take the 2 to the 3 and reduce it to a 2 to the maybe 3 minus 1 design by aliasing something, because otherwise there's no really good way to reduce that. And then 3 and 5 are also relatively prime and relatively prime to 2. So you kind of get what you get there, but at least you kind of can see how this could work in practice. Now, where was I going with this? Yet you can also subdivide regions into blocks, and you can then try to figure out, well, where the confounding is happening. And this is another interesting thing you can do, because what it'll do is you can add a block factor, and the block factor will be confounded with some interaction. So let's say I have this, and I say I want, where's the block in here? I think I want blocks, the number of blocks into which the experiment is subdivided. So let's say I want to turn this into 2. I want to split this into 2 blocks. Say, aha, well, there we go. Now what has happened? Yeah, these are annotations, not part of the data. So now we have a blocked factorial design. And if you notice, what we've done is we still have 120 observations, but we've broken them into 2 sets of 60 for blocks. So I have my first block with these guys. I think it's also randomized. So again, by default, it will always randomize all of the rows. And in this case, randomize the way that the rows are put into the 2 blocks. And we also have block 2 here. So in this case, we're good. I think we haven't run into any confounding issues. But, and again, let's see what happens if we try to do 4 blocks. Then I get a bunch of warnings. And what do the warnings tell me? Well, they say, look out, because your block is confounding a 2-factor interaction. And I guess that happened 3 times, probably because I have 2 blocks. Well, I have a 4-level, I have 4 different blocks, which is like a 4-level factor. And what it probably means is there'd be 3 degrees of freedom associated with that. And in this case, I'm probably confounding 3 different 2-way interactions of binary terms that each require 1 degree of freedom. So at least it'll warn you if you confound a 2-factor interaction. it doesn't warn you for anything higher because, again, typically we're not as interested when you get to 3 or higher order interactions. So I think it will confound them with the best of intentions. Now, I'm not actually sure what's going to happen, but why don't we try 8? Now, in this case, I think the only way it can do this to have a balanced block design would be if it just wiped out the entire 2 to the 3 design. Let's see if it gives, oh yeah, it just gives me an error. It just says, no, don't even, that's dumb. Don't do it. Yeah, too few factors with even numbers, because in this case, if I wanted to have a balanced design, the only way to do that would be to kind of obliterate the 2 to the 3 that I have already. All right, so what's the takeaway here? Well, there's a couple takeaways. The first is that you can use R to design your experiments, which is great because you can check for confounding, you can check for aliasing, you can do all of this before you go out and collect any data, and that's really the way that you'd want to do it. Now, there's another interesting thing, which is all these warning messages, and what it reminds us is that designing an experiment is hard and that you can't always get exactly what you want. I say, I have 8 different blocks and I have 3 different two level factors and 1 3 and 1 5. Well, it's just going to shoot out an error and say, no, I can't do that. It doesn't work. And that's one of the other things that I think is not always clear with design of experiments, is that just because you know how many factors you want to test and you know how many blocks you have and you know how many tests you can do per block and everything like that, you know what the sample size should be, doesn't mean that there's an experiment that will satisfy those conditions. So you have to be careful and you have to, well, carefully design your experiment before you start it. Now, that's more or less everything I wanted to talk about today. What we will be doing in the next lecture is we will be looking at the one thing that I didn't include discussion today from the FRF2 package, which is the PB function corresponding to the Plackett-Berman designs. And the Plackett-Berman designs are, well, they're interesting, right? They're going to be 2 to the 2 to the K designs, but they're going to have non-powers of 2 as their as the number of observations. So right, our 2 to the K, or our binary factorial designs, have one big issue, and that's you have to have a power of 2 for your sample size, which may not be possible. I mean, you may have enough funds to get 20 people in your study, and you don't want to have to go down to 16, and you can't go up to 32. So what do? Well, you could try a Plackett-Berman design. How do they work? Well, we're going to find out in the next lecture, so I'll see you there.